Let's discuss now the kind of responses that we should expect of a system if we know the transfer function. So we could entitle this discussion, uh, time response using, understanding time response using the transfer functions. Now, if you have a transfer function like this is a simple transfer function that has s plus 2 and then you have s plus 5. The first thing that we are going to do is to name these things. You have a polynomial on the numerator and you have a polynomial on the denominator. Okay? If you set s plus 2 to 0, then it follows that the root of that, let's say if you put the numerator, you set s plus 2 equals 0, then it follows that from here s is equal to minus 2. You see here, if in the complex plane we plot this is at minus 2. So this is right there, yeah? So this, we are going to call it a 0, just a name. As the root of the numerators are called 0. But if we set the denominator s plus 5 equals 0, it's very obvious that s is equal to minus 5. So if we plot the denominator here, this 0, this minus 5, this we are going to call it a pole. Okay? So you have a 0, which is the roots of the denominator, and you have a pole, which is the roots of the denominator. Okay? Now you see in here we have an input which is 1 over s. If you set the denominator to 0, then the root of the denominator, the 0 is right here, right? At the 0 point. Okay? So we have a situation where we have this 0 here. We have this pole over here, and we have this over here, the other pole. So when you have this, can we predict the time response of the system? Can we, or what would be our best guess of what the system is going to do? We could decompose this into these fractions, and by using the inverse Laplace transform, you say, okay, this has some constant value plus it will follow this term. But the easiest way, it seems to me, would be to go to MATLAB, enter the transfer function, and then look at this. So whenever you have a pole, the idea here is that this is going to generate this kind of response, yeah, over here. So if we can draw it on top here, this means this kind of response. This is of the type e to the minus at, like that. Okay, but I will take advantage of the fact that if you do it outside, let's say right here, not in the real axis, but here, where you have this component of the real and you have this component on the imaginary axis. This one is a combination of a decay like that and an oscillation. So you see, by knowing that a pole is here, this like I say is a pole, you say with real plus imaginary components. In this case, the response is going to be like this. So we are going to become experts at reading the complex plane to find out what the answer is. So in here, you have this response, and you have if you plot it in the time domain, here's what will happen. You will have a response that goes from 0 all the way to, if the input is 1, it would be like this. But we are going to study and give some names to some things on the response game. So the initial slope in here, 1 over that is the so-called time constant, which is a measure of how fast or how slow the system responds. Okay, so this is like a step input on a system. So we're going to test the signals. So what I would like to show you is that if you have this kind of transfer function, that you have the denominator, you are going to produce this response. If you have this kind, you will get this response. If you have it like this, you get like this. So I think it would be really helpful as we are starting this to try each one of the systems in MATLAB and show you that in fact they respond like that. Let's try that. So let's just put this in the background here, and I am going to go to MATLAB. I have it opening here. I think we need to work with something new. All right, so we're going to work with a new filing here, and what I'm going to show you is, first of all, how do we enter this transfer function here? And the way we do, first of all, is let's define the variable s as as a transfer function type of element. So S is going to be a symbolic file, like it's going to be like S is equal to SYM. So is like this, or we could define it as an individual transfer function element. But let's see where we go with this. So in here, if we could say the numerator is equal to we put the polynomial constant, this is 9 in there, like that, and then you have the denominator is equal to what do we have, 1 for s squared, and then the other one is what do we have, a 9s, right, 9, and the fixed term is the constant term is also a 9. So if you do this, and then you say do the transfer function for me between the numerator and the denominator. Okay, sorry, I have a bit of a syntax problem here. We need to give it a name. So g is the transfer function between the numerator and the denominator. And if you do that, you have defined what g is. And we should be able to get a response here. We have to run this, obviously. So if we run this, save, you see, this is the, you'll get the transfer function here. Sorry, I didn't want to, there we go. See, so we get this transfer function. All right. So this is the transfer function here. Now, can we get a response from this so as to verify that this system in fact is going to do that? So you're going to say a step of g like this. Hope you, and look what will happen. And that is in fact how it responds. You see, that is, this plot is like what you have right here. See, this is like this. But if you actually change this and the poles are no longer here on the real axis, but they are over here, let's say, just by changing the 9 to a 2, we will get a totally different response. So let's take a look at that. So let's go back to the MATLAB here, and then we are going to change this. Instead of a 9, we're going to make it a 2. Oh, I think it was a 3, right? Yeah, 3. And then if we run this, you'll get the transfer function. There it is. And then in here, we are going to say a step of the transfer function g. And I should see the plot. See, it's behind here. So let's move it so we can actually see what it's going to do. Yeah. So I am here, and then you please, and there it is. So you see it changed the way the system responds. My point, and I want to leave you with this thinking, is that if you change the transfer function and you move those poles, you can obtain a different answer. So I think the revelation here, I would say the main focus of this discussion is that if we have the ability to move the poles, we have the ability to change the system. That's the point. But not only the poles, the zeros too. Or could we do a combination of zeros and poles and make it do what we want? That's the center of this discussion here. I'll let you try the next one, although maybe it's probably just as good that we let's say all this has done is take this term away, the second term, and when you do that, you have the roots on the imaginary axis. So if we go to MATLAB in here, and instead of this 3, we put the 0, yeah, which is the same thing doing that, we will obtain a new transfer function here. Yeah, there it is. That transfer function is like that one, like this. Okay? And so if we try the same command that we have, this command is step, and watch what happens now. Oops, this gave me there are too many of those to see, but the response that we have is this one. It's just that you see so many of them. And here perhaps we shouldn't have the plot over here, but rather have a, a different one, so that a different step. But that's the idea, that you get a totally different response by changing this. So